All righty, good. So for the second talk of this session, we can see here we have a talk called Calculus for Amortized Expected Runtimes by Kevin Batz, who's standing here and is emboldened there. Benjamin Kaminski, excuse my pronunciation, possibly Joost-Pieter Katoen, I don't know, Christoph Matheja maybe, and Lena Verscht. Sure, sounds reasonable. So I hope I wasn't too far off. Excuse me, Dutch people, I butchered your names. Okay, so we'll, as usual, proceed. So Kevin, go right ahead.
All right, thank you very much. Welcome, everyone. So in our paper, we contribute a calculus that enables the separation logic style verification of amortized expected runtimes. Our main goal is the analysis of probabilistic data structures, and it will be a weakest precondition-like calculus that utilizes the so-called potential method for amortized analysis. And the main features of our calculus on one slide, it's compositional. It enables local reasoning by utilizing a quantitative variant of separation logic. We provide easy to apply invariant-based proof rules for the analysis of loops. And we prove the calculus sound with respect to an operational semantics. All right, now before we consider the calculus, I will recap the concept of amortized analysis. And for that, we consider this simple probabilistic operation C. So we first check if variable C is equal to S. If so, we flip a fair coin. With probability a half, we will consume 2 S units of time, and with the remaining probability, we do nothing. Then we always double the values of S, and after that, we consume 1 more unit of time and increment the counter C by 1. Now, we can clearly see this operation has a non-constant worst-case expected runtime of S plus 1. However, and this holds especially for data structure operations that you typically execute not only once but multiple times, considering the worst case runtime can be too pessimistic, in particular if those worst cases are very rare. So in amortized analysis, we are interested in determining what is called the amortized, which is basically another word for average, expected runtime of an operation like this if we execute it multiple times and put it into sequence. So for this operation, one can show that indeed its average or amortized expected runtime is upper bounded by a constant. So in terms of a picture, the situation looks like this. Here on the x-axis, we have the increasing values of C, and on the y-axis, we have the expected runtimes of the different executions of this operation. And we can see that we have many cheap executions and actually rare expensive executions. Since we keep doubling the value of S here, those gaps increase exponentially. And as a consequence, if we sum over those green bars here, the amortized expected runtimes, this always upper bounds the sum over the red bars, the actual expected runtimes. Now, Tarjan in the 80s came up with an elegant way to analyze this. He says, let's say the following. For the cheap operations, we pay a bit more, so that whenever we encounter an expensive operation, we already compensated for that. So what we are going to do is we redistribute those expensive runtimes here onto the cheap ones. And this redistribution of runtimes is realized by fixing an appropriate, what is called potential function. So a potential function assigns a number, a non-negative number, or potential to every program state. And we must choose the potential function in such a way that the potential slightly increases in expectation for the cheap operations and drastically decreases in expectation for the expensive operations. We then define the amortized expected runtime of an operation as its actual expected runtime plus the expected change of the potential caused by executing the operation. And this expected change will be slightly positive for the cheap operations, and it will be negative for the expensive operations. So in this particular case, one can show this is indeed upper bounded by a constant. And importantly, one can then show that if we start with a potential which is initially 0, this is the case for my picture here, then the actual expected runtime of a sequence is upper bounded by the amortized expected runtime of the sequence. And this formally underlines that instead of summing over the red bars, we can also sum over the green bars. All right, so this was a toy example for illustration purposes. In our paper, we also considered realistic examples taken from the literature. And we considered, for instance, the so-called Insert-Delete-FindAny problem, which is due to Brodel et al. So the problem is as follows. Suppose we want to maintain a dictionary data structure D, storing numbers, that provides standard insert and delete operations. And additionally, this data structure provides an operation called findAny. And findAny is supposed to return an arbitrary element y from the data structure together with its rank, which is defined as 1 plus the number of elements in the dictionary that are strictly smaller than y. Now, remarkably, Brodel et al. Show that there is no deterministic implementation that can run in constant amortized time. However, they also show that if one utilizes randomization, then we can achieve constant amortized expected runtime. So we see in order to analyze a data structure like this, we need a calculus that can deal with randomization. We need to apply amortized analysis. And we also need to be able to deal with pointers, since these operations are actually implemented using doubly linked lists. So we took the randomized operations by Brodel et al. And modeled them in our imperative programming language. And I will not go very much into the details, but I want to emphasize we have probabilistic constructs. Here, for instance, a probabilistic choice. Or here we sample uniformly from the doubly linked list in the heap. And we have pointer operations. So here, for instance, we access the value of a memory cell in the heap. And using our calculus, we are able to prove purely by reasoning on the source code that these operations are indeed memory safe and run in constant amortized expected runtime. Good. So next we consider the calculus. First, very briefly, this is the programming language we are considering. There's nothing really special here. So TIC-E models time consumption of E time units. Randomization is introduced by this probabilistic choice statement here that says with probability P, execute the left branch, and with probability 1 minus P, execute the right branch. And we also have standard pointer operations that we will ignore for the moment. Good. So when using the potential method, the first thing that we have to do is fix a potential function pi, which is a map from states to non-negative numbers. And once we did so, we consider the complete lattice of what we call pi runtimes. So these are the central objects that our calculus operates on. And a pi runtime just assigns a runtime to every program state. Now, importantly, in amortized analysis, runtimes can be negative, but they cannot be arbitrarily negative. In fact, they are lower bounded by this potential function pi. And if we then order these runtimes pointwise in the usual manner, we obtain a complete lattice. Good. Yeah, and our goal is now to define for every program C, in fact, compositionally by induction on the structure of C, the aert of C with respect to the potential function pi. And this will be a runtime transformer mapping pi runtimes to pi runtimes in such a way that if we consider the aert of C with respect to what we call the post-runtime 0, this is again an object of this type, right, mapping states to runtimes. So if we plug in an initial program state, then what we get is the amortized expected runtime of C with respect to the potential pi on the initial state signal. So why do we need this post-runtime 0 here? This is due to the fact that we employ a continuation passing style to define the aert. Now this is very similar to what you know from weakest preconditions. It works like this. Suppose we want to determine the aert of this composed program C1, C2. We will do so by analyzing the program backwards. So we start at the end of the program with post-runtime 0, which reflects that on termination we consume no more time. And then we apply the aert to C2. This will give us the amortized expected runtime of C2. And this will then be our new post-runtime that we use to apply the aert to C1. So that in total we get the amortized expected runtime of C1, C2. So in this sense, our calculus is compositional with respect to the program that we analyze. And additionally, in our paper, we also show that it's compositional with respect to this potential function pi here. And this works as follows. Suppose we are given two data structures, D1 and D2. Data structure D1 requires potential function pi1, D2 requires potential function pi2. And now suppose we would like to analyze a composed data structure that uses both D1 and D2. In our paper, we show how this can be done compositionally by first analyzing the individual data structures and then reusing those analyses for the composed data structure. Okay, so this is now the inductive definition of the aert with respect to some arbitrary post-runtime x. And for the tick statement, this is easy. So tick e consumes e units of time, so the aert is given by e plus what is given by the post-runtime. For assignments, it works as follows. We first apply the assignment to the post-runtime by substituting x by the right-hand side of the assignment a. And then we have to take the change of the potential into account. And this is what happens here. So the new potential is given by pi, where we substituted x by the right-hand side a. And from that, we subtract the original potential pi. And this is how we add the change of the potential here. Probabilistic choice is also quite intuitive. We first determine the aert of C1 and C2, add them up, and weigh them according to the probability of C1 and C2 being executed. Sequential composition is, as I've shown you on the previous slide, 4 conditionals. So this is the indicator function of the predicate phi. So this rule says if phi holds, consider the aert of the first branch, otherwise consider the aert of the second branch. And finally, maybe surprisingly, even though we deal with possibly negative quantities, which is known to cause integrability issues in the probabilistic setting, we can define the aert by means of a least fixed point. So no integrability issues here. Intuitively speaking, it reads like this. If the loop terminates, take the post-runtime into account and otherwise recurs on the loop body. And since we can apply this least fixed point construction, in fact, we obtain easy to apply inductive proof rules for the analysis of loops. And in our paper, we have some illustrative example where we demonstrate these inductive proof rules. All right, so let's now apply the aert to an example. So here we have another probabilistic operation. With probability a half, we consume x units of time. With probability a half, we set x to 0. And then we always increment x by 1. So once again, this operation has a non-constant worst case expected runtime. However, if we execute this operation multiple times, then expensive executions will be so unlikely that this operation in fact runs in constant amortized time. We will now prove this using the aert calculus. So the first thing we have to do is fix a potential function, in this case x. And then we start at the end of the program with post-runtime 0. Now we encounter an assignment. So we apply the assignment to the post-runtime. This has no effect. And then we have to take the change of the potential into account. New potential is x plus 1. Old potential is x. If we simplify, we get an aert of 1. And this will now be our new post-runtime that we use to determine the aert of the 2 branches of this choice. So we start with this lower branch here. Again, we have an assignment. We apply the assignment to the post-runtime. This has, again, no effect. And then we add the change of potential. New potential is x, 0. Original potential is x. And if we simplify, we get 1 minus x. And here we can see this is actually an example where we even possibly get a negative aert. So even though we assume that x is a natural number here, this expression possibly evaluates to a negative number. Good, now we deal with this first branch here. Post-runtime is 1, tick x consumes x units of time, so we get x plus 1. And now we can compose the aert of the 2 branches. We get the following. With probability a half, we get x plus 1. With probability a half, we get 1 minus x. And if we simplify, then we see that indeed this operation runs in constant amortized expected time. All right, so for now we ignored pointer operations. So I will show you now how we can incorporate dynamic memory into the aert calculus. And this basically works by utilizing what is called runtime separation logic, which is due to Christoph Matheja and Max Haslbeck. So we will now pay attention to these standard pointer operations here: allocation, lookup, mutation, and deallocation. And we will assume a standard stack heap model. So in particular, a heap is just a finite map from locations to values. And importantly, we assume that memory faults cause an infinite runtime. Now that's our memory model here. Now, what's the main idea underlying runtime separation logic? So the basic idea is to define separating connectives on runtimes. So here, for instance, we have the separating addition, and this is the quantitative analog of the separating conjunction. And it works very similar. So we take the minimum over all possible partitions of the heap, then we sum f and g, evaluate f in the first and g in the second heap. So we also have this splitting of the heap here, and standard conjunction is replaced by this quantitative addition. Intuitively speaking, conjoining two runtimes means adding them up. And you can also define a corresponding adjoint. This will be the quantitative analog of the separating implication, but I will omit the details here. Now, a typical runtime specification then looks like this. It says, okay, if x and y point separately to 1 and 2, then the aert is upper bounded by 3. So more precisely, this expression here evaluates to 3 if the stack and the heap are indeed of the desired shape, and otherwise those gatekeeper brackets, as we call them here, will evaluate to infinity. Good. This is now the definition of the aert for the pointer operations. I will not go much into the details, but you can see this is very close to standard weakest preconditions for separation logic. So for instance, if we consider the rule for memory deallocation here, the rule says, okay, E must be allocated in the heap. If this is not the case, this expression will evaluate to infinity, which is what we want. And otherwise, we will evaluate this sub-expression here in the sub-heap where we excluded E. And again, we take the change of the potential into account. This happens by evaluating this instance of pi only in the sub-heap where we excluded E. Basically, the same intuition holds for the other constructs. And then, importantly, the aert is defined in such a way that we either get the amortized expected runtime of C, if C is memory safe on the given initial state, and otherwise the aert will evaluate to infinity. So in particular, if you can prove that the aert is finite, this already implies that the program is memory safe. So one open question was, is this indeed the case? So does the aert indeed always provide us with the quantity we're interested in? And we have proven this with respect to an operational Markov decision process semantics. And schematically, it looks like this. We start in some initial state, and due to the randomization or the non-determinism, we have possibly multiple executions. Some might add up in a memory fault, some might diverge or terminate successfully. And then every run is assigned a cost. So runs that end up in a memory fault are assigned cost infinity. The cost of all remaining runs is determined by the tick statements occurring in the program C. And then one can prove that indeed the expected cost, which is given by this operational model, is always upper bounded by the aert plus the initial potential. So in particular, if we start with an initially 0 potential, the aert always soundly upper bounds the expected cost given by our operational model. All right, so finally back to our case study, the insert-delete-FindAny problem that I've shown you in the beginning. Here is again the source code, and using our calculus, we can now, very similar to standard separation logic proofs, analyze the amortized expected runtimes of these operations. So we can prove that indeed they are memory safe and run in constant amortized expected runtime. And the main ingredients we need for that are, first of all, inductive runtime invariants for loops. They are not always easy to find. This invariant, for instance, evaluates to the length of a sublist in the heap. Then we need the aert frame rule. I did not show you this, but the aert features a frame rule which, under the usual side conditions, basically allows you to frame away runtimes. And then we have some additional rules for local reasoning, in particular for avoiding this quantitative magic wand, which simplifies the reasoning a lot. And this concludes my talk. Thank you very much.
Okay, thank you very much for a nice talk. Do we have any questions? Just raise your hand so I can see you. Okay, Ankush.
Do you allow for negative potential?
So the potential function cannot be negative, but the change of the potential can be negative. Yeah.
And maybe a related question then, when you end the program, your postcondition is always 0 with the aert?
Yeah, so assuming that after that we execute no more operations, we always start with 0 or end with 0. And this will give us the amortized expected runtime. Yeah.
Are there situations where you may not end with 0 because of branches or other sources of problems?
Yeah, exactly. So in particular, if you analyze a composed program, then the, let's say, post runtime of the first one will be the aert of the second one. So that's exactly how this compositionality comes in. Yeah.
Thanks.
I have a question.
Yep.
What are the prospects of extending your analytic methods to parallel programs?
Yeah, I think that's an intricate question. I think this poses challenges. I can't tell you off the top of my head. So my colleague is working on parallel programs. Maybe he could say more, but...
Jan Hoffmann, Carnegie Mellon. Yeah, very nice work. I enjoyed the talk. A question I had is like if you have a global potential function, is that limiting in the sense that like if you have a program that has maybe 2 loops and sees the same state again in the middle, maybe you want to switch to a different potential function there, and yeah, can you comment on that?
So sorry, I didn't get the middle part.
Oh, if you, yeah, this doesn't seem to.
No, I think it works fine.
Oh, okay. Yeah, if you have a global potential function, is that limiting? So do you want to maybe switch, to a different potential function somewhere in the program? If you have one loop over x and then another loop over x, and then maybe you have to switch to a different potential. Yeah.
So we didn't encounter this case yet. It might be. But what we encountered is this, that we have 2 data structures, right, that need different potential functions. And in this case, we have a proof rule where we can reason compositionally about composed potentials. So maybe this rule is also applicable in that case, but I'm not sure. Yeah, thanks.
If I'm not missing anyone, I don't think there are any more questions. So let's thank our speaker. Thank you.